Things just coming together and working perfectly.
All right, so thanks everyone for coming today. I hope you all had a great week. Today we have the pleasure to host Ross, who is a research scientist at Google DeepMind here in Montreal, and he'll share with us some thoughts on course-correcting Koopman representations. So before handing the mic to you, Ross, let me remind you all of some house rules. As usual, clarification questions will be allowed to be asked during the talk. For people in person, you just have to raise your hand and wait for me to give you the mic so that people online can hear you. And for people online, you just have to type the word question or I have a question in the chat, and when the time is right, I'll let you directly ask it. There'll also be some time at the end of the talk for people to ask further questions, make some comments, and have a more informal discussion with Russ. That's pretty much it for me. Whenever you're ready, floor is yours.
Thank you. So the first thing is, I should say, we should learn to pick, more eye-catching titles. There's, yeah, maybe it's a little too late now, but so this was a work mainly led by Mahan, who's my former intern and Mila student, and also in collaboration with Pierre-Luc's lab. Okay, so let me just try to motivate the problem. And then I'll say a comment about the slide a little bit after I get the motivation out of the way. So this talk will be ultimately about future prediction of physical systems. So we want to be able to sort of reliably predict, in some sense. This is a very messy problem because it involves partial observability, non-determinism, but we're going to focus on a very narrow, very isolated part of this problem, and we won't tackle a lot of it. So essentially, if you want to do kind of reliable future state prediction, you might have, for example, computer vision, which extracts some sort of state from your system. So in this case, you might have a picture of a billiard table, and the state might be, the position and initial velocity of all the balls on the table. Then you might have some model, which kind of rolls things forward, which represents the physical dynamics. So in this case, it might be like Newton's laws, Newton's equations represented as a system of ODEs. And then you might take the state, and if you wish, you can render, a frame. And this is just kind of like a funny example of how things break. Like I'm telling you, the position and velocity of these billiard balls, and everything is very neat. And along comes this billiard ball at 400 miles an hour and just smashes everything to pieces. So good luck. predicting that, right? So in this talk, before people start rolling their eyes, it's not going to be a talk about, convincing you to replace transformers with differential equations or something like that, or something silly like differential equation solvers. So it's not going to be a talk of that flavor. But so what we will focus on is just this very isolated, very neat, like much more neat than, in the wild typical machine learning problems. So we're going to assume that we have a fully observable state, which represents the conditions of some dynamical system. And we're not going to assume that we know what that dynamical system is. All we're going to assume is we have observations from it. So we collect, sequences based on different initial conditions, trajectories in the state space. So this talk is going to be about modeling this very isolated kind of like more or less neat aspect of the problem. Okay, so let's get the problem statement a little bit more formalized. So given a sequence of observations from a fully observable deterministic dynamical system, come up with a model of the system which accurately predicts future states. And we'd like this model to have two properties. It must be we're machine learning people, so we want to kind of learn a model in a data-driven way. So we're going to just have access to trajectories without any knowledge of the system. And also when we have, for example, sequences of, let's say we collect sequences of length 100, a good model should be able to generalize beyond that length, right? It shouldn't just fit the training set. It should be able to unroll to sequences of 1,000, for example, and still have accurate predictions. And that's how we'll sort of evaluate our model. Okay, so before I get to the next slide, when I say we have a state and we're going to learn a model of that state, and we're deep learning people, at some point we're going to want to perhaps extract features from that state. Instead of working in the original state, for example, the position and velocities of all the particles, we might want to find patterns and representations of it. And so we might want to extract some features, like if we push it through a neural network, the first thing it'll do is kind of like move to some other feature space and do some other black box processing on top of that feature space. Also in this feature space, we might want to impose some properties on it, like some sort of regularity. So for example, if trajectories in the original space are very curved, we might want to, impose kind of like low curvature, simpler trajectories. Maybe the trajectory should be described by a simple dynamical system in this latent space. And at this point, man from 1931, Bernard Koopman, has something to say. So in 1931, Koopman proved something that's sort of analogous to the kernel trick for dynamical systems. So basically showed that there exists a set of features. Back in the nomenclature of the day, they were called measurement functions. There exists a set of measurement functions such that when you extract those measurement functions from the state, the dynamics in the space of measurement functions are linear. Now, a lot of people might be asking questions like, sure, constant is also linear. Like you can have degenerate solutions. We'll get to that. But also a caveat of what he proved is the fact that phi might need to be infinite dimensional. So similar to the kernel trick, you might need to kind of like move up in dimension and possibly even uncountably infinite dimension. So I won't get into the kind of like hardcore math of this. There are other papers, plenty of papers on this. But I hope this part is clear of what it's trying to do. And also, one thing I should mention is, we have dynamical systems, which could be continuous time or discrete time, and we can kind of like move from continuous time to discrete time without without major hiccups usually. So any questions so far? Yeah.
Is phi invertible in general, or
Not necessarily.
necessarily?
But we'll have our own formulation of this, and we will try to make it be invertible.
Okay, thanks.
So how do we take this idea and sort of, well, this idea involves infinite dimensions, and we don't want to get into the whole like kernel trick right now. Let's just have like a finite approximation to this idea. And the finite approximation is a simple autoencoder. So we can train to learn such features if we introduce an encoder which takes us from the original state space to some latent space. We'll also train a decoder that takes us back. So this will kind of ensure invertibility or encourage invertibility. And also we'll have this nifty little second term in the loss, which we call the alignment loss, but other people have used this as well. I think they call it alignment as well. And this will basically encourage that the transitions in the latent space will be described by a linear dynamics. And we're also going to learn the linear dynamics, which is given by matrix K. So you basically choose some higher dimension of phi. So n is larger than d, inspired by the Koopman sort of theorems. And hopefully we can train this encoder, decoder, and transition matrix K. Okay, so I hope that's clear. This is all pretty vanilla. This is like deterministic stuff. There's no VAEs not needed. Okay, so let's say we have this encoder, decoder, and transition matrix K. How do we use it? There's some design choices. So I can take some initial condition X, encode it, get some initial feature representation in the feature space Z. Then I can, if I believe the dynamics are truly globally linear with in the Z space, I can hit this with K as many times as I like and get a trajectory in the Z space. And then of course I want to go back to the X space to evaluate how well I'm predicting. And then I could decode all of these and get a trajectory in the corresponding trajectory in the X space. Alternatively, I could do the following. I could encode, get the initial Z, move forward in time with K, get the next Z, go back to X, re-encode X, and kind of use the encoder and decoder at every step. So far, it seems like, well, sure, you could do one or the other. It seems pretty arbitrary. So let's look at now some toy examples of results. So at first, to us, it also seemed like, well, you can do one or the other. And also, but before I get to the next slide, of course, there's a middle ground. You could like re-encode once every so often. Okay, so this is a famous dynamical system called the Duffing oscillator. It's described by a second order differential equation, so x double dot x minus x cubed, which you can convert to a system of first order. You could do this with every higher order ordinary differential equation, convert it to a system of first order differential equations. So you really have a dynamical system, which is like, as I written here, x dot equals f of x, right? So you just make a new variable. So x1, the first x, that's the horizontal, will be x, and then x2 will be x dot. And then you have an expression for how x1 changes, for how x2 changes, and it's a matrix. So so I hope it's clear where x1 and x2 come from. And the interesting bit about this dynamical system, it has 3 fixed points. One is unstable. It's at the origin. So that means like any perturbation away from the origin, you'll either shoot off in one direction or another. There's 4 directions you can shoot off to. Anyway, the full, more or less, ground truth system evolved according to the real differential equation, or the dynamical system looks like this, more or less. The ground truth is actually in light gray here. Let's check the time. Okay. Question?
Yes, you can ask your question.
Hi there.
Mhm.
I was just wondering in your previous slide, if you can go. Yeah. So number 1 and number 2 are actually referring to equation error and output error models.
Equation error and output error. No, so these aren't two-way. Yeah. So in both of these models, we will evaluate them in the same way. We will evaluate future predictions in the X space. We will never evaluate in the Z space. It's just two different ways of unrolling a model. One is doing unrolls in the latent space, and the other one is kind of recursive, like constantly going back to the observed space and the latent space at every step.
So it's not about forecasting or predicting the series or the sequence of events multiple times from the first step or observation. So what you're doing in model number 1 is you take the input and then you forecast multiple times without finding the output error.
Yeah, okay, yeah. This is an important point. So this is not teacher forcing, and we say this in the paper. So this is very different from teacher forcing. We never use the ground truth X in the second case. We simply use the encoder decoder, so we have a predicted X. We re-encode it. We never actually inject the ground truth. Is that your question? I believe that's what you're trying to hint at.
Yes, so that actually equation error and output error models, I'm referring to the concepts in basically control engineering concepts for modeling dynamical systems.
Okay, I'm not familiar with that terminology, but
so basically we can forecast. So, but you're saying you're not forecasting here.
No, so both plots are forecasting. They're just using different ways of forecasting. It's like a design choice. So
what I'm referring to is the first way of forecasting is you basically take the input and then you keep forecasting, let's say, k steps ahead.
Yes.
So in the second method, you take the last k steps, which is one observation, and then you forecast the next k steps. So,
no.
So that's like one step. The second scenario is indeed one step ahead forecasting, but the first scenario is multiple steps ahead forecasting.
No, they're both multiple steps ahead. They're just different ways of generating that multiple steps.
Yes, but the second scenario is also kind of multi-step ahead because you're forecasting, let's say, 7 steps ahead, but you're actually taking the previous 7 steps and then forecasting the next 7 steps. But in the first scenario, let's assume our state has only one dimension, right? So we take that one dimension and then we forecast the next 7 observations. But in the second scenario, the input has 7 dimensions, which is the past 7 observations, let's say. It's rough and inaccurate, but I just want to transfer what I'm trying to say. And then we forecast the next 7 observations. So although the second scenario is forecasting the next 7 observations, it is still using a model that does one step ahead forecasting.
Yes.
So I was wondering if your number 1 scenario translates to the first scenario that I said. We take the observation and then we forecast k times, and the error actually propagates in the first model. The issue with the first model is that the parameters of the model that fits such model, if it's basically estimated by a linear estimator, right? It deviates drastically. So if you want to, let's say, fit a model here for the first scenario, the model parameters become non-linear, although the model considered as linear. And with the second scenario, the model remains linear because there's only one input. But here we have multiple, basically, inputs, and the inputs are actually feedback to the system in the first scenario.
Yeah, I think you're you probably have the punchline in your head, but maybe I'm going to present it in slightly different way. Does that make sense?
Is this the same? Are these two the same concepts that I said, or these are two? You're putting two different models there.
No, so just imagine it this way. This is the same model in the sense that it has the same, both the left picture and the right picture have exactly the same trainable parameters. It has an encoder, decoder, and K matrix. And it's a black box, and I'm not telling you how I'm going to generate these future X's. So as far as the predictions are concerned, we require the same inputs and produce the same outputs in both of these. It's just how the black box is working underneath that's different. So behaviorally, they behave exactly the same. Like they both get only the initial X as input, and they produce all the sequence of future X's. But how they generate that prediction is different. Sorry, I'm not sure if that's clear, but
That's fine. It's all fine. I don't want to take too much of time
But
on
we can-
their
feel free
participants.
to ping me afterwards, and we're happy to chat offline.
Really appreciate it. Thank you, sir.
Okay, no problem. Yeah. All right. So the left side, we have the trajectories corresponding to no re-encoding. The right side, the middle picture is re-encoding at every step, and the rightmost side is periodically re-encoding. That means like we have a hyperparameter, and then we tune it for the system, and we basically say, okay, we're gonna go back to the observed space every, let's say, 10 or 20 steps.
How was this trained?
Yeah, it was trained on just pairs. There was no sequence training. It was just trained on just one step, and then we're unrolling for, I don't know, I'm not sure what this one is, but it's in the paper. So we make sure that we have train and test initial conditions. So we never, we have a split train validation test. Uniformly in the space, because it's just two-dimensional, so it's just.
Excuse me?
Yeah.
I was wondering, what is the intuition between re-encoding working better than no re-encoding? Yeah.
That's going to be like the math. It's coming up.
Thank
It's not just empirical results. Yeah.
Do you know what the value on the right side for how many steps you're doing?
I believe it's like 500. I don't remember
Okay.
Offhand.
Okay.
For this.
Yeah.
So you can do this for, this is an interesting system because it has multiple distinct attractors. This is nonlinear, but it has just a single attractor. This is another famous dynamical system, and you could do this for lots of them. Okay, I won't. But basically, you have the same sort of repeated phenomenon. No re-encoding is kind of the worst. Re-encoding at every step, yeah, it's starting to look a bit right. And by the way, this light gray is the ground truth, but periodic re-encoding works much, much better than everything else. Okay, question is why? The first thing to notice, for those of you that are keen about dynamical systems, there's something very wrong with the phase plots when you don't do re-encoding, in that they cross. And for fully observable deterministic dynamical systems, phase lines should never cross, because basically where they cross that crossover point, they can merge into each other. So you can have an attractor. But if they ever escape and kind of like you have a point and you have two sources, that should never happen, because from the same initial condition, you should always get a deterministic single trajectory. So something is very wrong with no re-encoding. What's going on? Okay, so without re-encoding, you can write some math, and this is what's going on. You take your initial condition, you encode it with the encoder, you get your initial condition in the latent space, and then you're assuming globally linear dynamics. You're assuming that. That might not really hold true, but you're assuming that. And this equation with this initial condition has a closed form solution, because this is just a linear dynamical system. The solution is the matrix exponential k multiplied by the initial condition. Okay, and now when you have this, so basically you have a dynamical system, a linear dynamical system in the latent space, but to go back to the observed space, you take that entire solution and map it back with your decoder psi. In the second case, if you re-encoded every step in continuous time, it's a feedback, right? It's a mapping from your current x that will tell you your derivative or your next x in discrete time. So it's constantly a feedback loop, which is at the heart of dynamical systems. So basically, the way you derive this equation is just differentiate x dot, get x dot. And so this is just the Jacobian of psi multiplied by the matrix K, multiplied by the initial, by the current code, which is the encoded state. Okay? But the important thing to notice is just x dot equals, some function of x. So it's a real dynamical system. So in the top equation, we can see why things cross. Unless this mapping is somehow guaranteed to be injective, you're basically taking solutions of linear systems and squashing them into the observed space. And usually it's a mapping from higher dimensions to lower dimensions. And of course, things were going to kind of collapse onto each other. This is like a picture that Mahan drew. Like, yes, in case it's not clear, you're taking, a trajectory, which we define as never crossing on itself, and you map it, and it can like kind of double over on itself. Okay. And this, by the way, is not unique to only latent linear dynamics. This applies to any latent dynamics. So even if you say, oh, but my latent dynamics, let's allow them to be nonlinear, you'll still have this problem. The only difference is you won't be able to write the closed form solution explicitly. It'll be some function, let's say some solution, which is a function of time and your initial condition. So let's call it H. But then you're still taking this thing which we know won't cross itself, and you're decoding it, and it's likely to cross itself. And similarly, if K is no longer, let's say, a matrix, it's some function. It's that takes the Z as an argument, which is the encoding of X. This equation still holds. So this will always generate valid trajectories that won't cross, and this it's not guaranteed that they won't cross. Okay, so basically this is kind of true beyond latent linear dynamics. It's not a particular issue with latent linear dynamics. It's basically the most succinct way to say it is, if you're modeling a feedback system, you should probably model it with a feedback process. That's like a good inductive bias. So it's basically what you're doing in the first case is you're trying to use nonlinear functions to model a nonlinear feedback process. Okay, you can have this image in like continuous time. So basically, for a while, you might go along with sort of linear dynamics, which you can calculate explicitly with the matrix exponential, then sort of re-encode, then for a while again, go into linear dynamics in the latent space. And so if you do this for short enough time and your dynamics are smooth enough, they won't have time to cross themselves, essentially. So it acts as like a nice regularizer. So that's why periodic, yeah.
So what I'm wondering is that K is not the ground truth, right? You're learning K and you're learning phi. There's some finite dimensionality, so this can't be exact, right?
Yeah.
I'm missing on why it wouldn't cross in one case and it would cross in the other case. Can you elaborate a little bit?
Cause what?
The path will cross.
I see.
Again, it's not
Okay,
crossing.
so in the second, so basically for any dynamical system, any feedback process, you're guaranteed, if you integrate this out, you're guaranteed, unless it's discontinuous or pathological in some other case. If these are continuous, nicely behaved functions, Lipschitz continuous, things won't cross on themselves, just by virtue of you using a feedback process to generate this curve. Just like these trajectories, the ground truth dynamical systems, which are generated with differential equations. I mean, this almost looks like the ground truth. Sorry. In latent, but not in the observed. Like once you, I get your question. I need to think about it, but basically, if you have a dynamic, basically what this thing is, it's a dynamical system. And so if you're generating the trajectories of the dynamical system, it won't sort of cross itself unless it's discontinuous. There's another question.
Yeah, Jeffrey, you can ask your question.
Hey, yeah, this is really cool. So you've shown that you're not going to cross each other, but looking at the plots, they go from looking totally wrong to looking pretty darn close to right. Do you have an explanation for why that might be happening? Like why this extra constraint is enough to get us accurate simulations?
There are two, so I've only so far talked about this crossover thing. There's a totally different phenomenon, which I'll discuss in the sort of second part of the talk, which also advocates why re-encoding is necessary. And so
thank you.
both of these things could be contributing. So we'll talk about multi-attractor, capturing multi-attractor dynamics in a few minutes. Okay.
Thank you.
Yeah. Okay. So, not in a few minutes, right now. And now for something completely different. Okay, so we're still going to talk about this topic of re-encoding and dynamics and whatnot, but forget about the crossing over itself issue. I hope I've convinced at least some of you that it's a real issue. There's a completely separate issue, which we perhaps rediscovered because then I kind of read a paper from 2013 and they sort of mentioned it as well. And I'm like, oh, well, okay. But it was from math, so it doesn't count unless it's machine learning it. Yeah. Okay, so in order to get to the second issue, let's do a quick review of linear dynamical systems. So first thing, if we have a linear dynamical system, take like any matrix A, let's say you draw it from a nice distribution and maybe the eigenvalues are somehow guaranteed to be less than 1 and or whatever. It could be greater than 1, doesn't matter. Take a bunch of initial conditions described by X, recursively hit it with A, and plot the trajectory of points you'll get. You'll get families of curves that look like this, depending on the eigenstructure of A. So if A is full rank, you'll have only one fixed point at the origin, always at the origin, unless you move the origin with like minus x0. If A is less than full rank, you'll have, I forget what it's called, Guillaume, you can tell me, like a line attractor. Okay, so things will like collapse onto this line, but the important thing to note is because it's dictated by the eigenstructure of A, it can't be like 2 lines or like 2 separate points. It's always connected, like topologically. Planes, yeah, in higher dimensions. Yeah, planes or lines. Okay, so that begs the question, which we originally asked when we started working on this, like how do you learn a feature space, let's say, of a multi-attractor system, such that the latent dynamics are described by a linear dynamical system, which can only at most describe like connected, like one topologically distinct attractor. So it was like, okay, something seems weird. So yeah, so that's the question. So in this case, let's consider this system or something that looks like this system. Forget about the attractor in the middle. For this tour example, let's pretend that we only care about modeling these 2 attractors on the left and right side. Let's take a tour example. So in this example, we're gonna consider only linear decoders. So our encoder is allowed to be any deep neural network, transformer, whatever you like. Our decoder is only allowed to be a linear function. And we're gonna, inspired by Koopman, we're gonna use a higher dimensional latent space. In this case, we'll use 4 dimensions, whereas the Koopman stuff used, whereas the original space is just 2-dimensional. So imagine, I'm not saying that this will happen, but it can happen. Imagine the encoder learns a sparse code, and it represents the left attractor with a code that looks like this. So basically zeros on the right, non-zeros on the left. So the support is like this. Whereas for the right attractor, which is in region 2, the right region of the state space, we'll learn a sparse code that looks like that. Now, it could also happen, hypothetically, that when we learn K could be block diagonal. And so if K is block diagonal and we hit K with these Z's, the support doesn't change, right? The zeros stay 0. And so you have basically 2 distinct linear systems that approximate this nonlinear system. So basically, we'll have a linear system here with an attractor here. We'll have a linear system here with an attractor here. They could have totally different eigenstructures dictated by K1 and K2. And then when we want to shift the origin, we can do that with the decoder. We hit it with the linear matrix K. That's exactly what's happening in our experiment. Basically, this experiment, I didn't tell you, this particular one uses a linear decoder, but we tried with nonlinear decoder and we get roughly the same behavior. Yeah.
So this predicates that you need to know a priori the number of ergodic components in your dynamics, right? So
this is a toy example of like what could happen. I'm not saying like.
But you have to make a choice for the embedding here, and so is that a hyperparameter, or do you have a like way to decide how to embed?
So one such general model is basically a sparse Koopman autoencoder. So you can have like choose a very high dimensional state space.
Yeah, just big enough so that
you have enough
things.
attractors to cover the whole state space.
Yeah.
And then you say you have a sparsity penalty on Z that says I want this to be as many zeros as possible, as sparse as possible. And then you'll get like the most parsimonious description of your nonlinear dynamics as a union of linear dynamical systems.
Got it. Makes sense.
Okay. So, but that's not even the most interesting part. So like, okay, so we have this thing, but what about re-encoding, no re-encoding? And here's the cool bit. If you don't have re-encoding, once you've committed to a particular support, you're bound to that support for forever. So basically, once you get an initial condition, you're going to stay with the same linear system forever. You can't switch between linear systems. So eventually, you'll go outside the region of where that approximation is valid, but you'll never get to switch. And so another totally different reason for re-encoding is if you interpret what's going on as these things are using sort of unions of linear systems to approximate a nonlinear system, is the ability to switch from one to the other. And so this is another way of looking at the same thing, is this thing is just a squished version of a bunch of linear systems that are kind of like roughly trying to approximate a nonlinear system. Here's the contrapositive of this point. So I said topologically distinct attractors require re-encoding. What if we have a nonlinear system which has a topologically connected linear attractor? Does it not require re-encoding? And the answer is yes. So there's like a sort of this toy example that folks came up with in 2014 that is like a closed form solution to the Koopman feature problem for this toy problem. So you have a nonlinear dynamical system. Just by adding an additional feature to the original features, which is the square of one of the variables, you have this linear dynamical system in latent space. And when we do the experiments with or without re-encoding for this particular system, it doesn't matter. It gives the same results. Yeah.
Thank you. So the encoder decoder are not assumed to be like they're inverses of each other, because if they are, it wouldn't matter, right? If they're or not, you're in the.
It's an important point. So they're not exact inverses of each other, and that's why we're advocating for sort of like the most shaky part of this work is why isn't re-encoding at every step not performing the best? Why is periodic re-encoding performing the best? And we don't have like a bulletproof explanation of this. We kind of have a hand wavy explanation, and it is the fact that they're not perfect inverses of each other. So you might want to like use it sparingly. I don't know, to be honest, but yes, they're not perfect inverses of each other. Okay, and now we have like results. So these are for like toy dynamical systems in like low dimensional state spaces. And Mahan did a very comprehensive set of experiments where we really tried like Wild West, like everything most things that we could think of. So the most direct thing you can try to do is forget this whole like encoder, decoder, latent states business. Just train an MLP. Just train an MLP to predict the next state, unroll it for a long time. That's terrible for some reason. Doesn't work that well. Okay, then you can kind of go one step away from that. You can say, okay, we'll do this encoder, decoder, like alignment business, but maybe the latent dynamics don't have to be linear. Maybe we can use an MLP there. And it turns out that that works best. But then how do you distinguish like where this MLP ends and like the decoder begins? Well, that's where you apply the regularizer. And it turns out in our experiments, the best place to apply the regularizer is right at the penultimate linear layer. So it turns out the best results we managed to get use the linear decoder and a non-linear, very heavy encoder with this alignment regularizer. Yeah, that tended to get the best results with periodic re-encoding. Okay, then I guess the next question might be, and then we could like, yeah, sorry, question. Question?
Yeah, you can ask a question.
Sorry, could you please go back to your results that you just showed? Yep, appreciate it. So you're actually showing multi-layer perceptron architecture here, right?
On the rightmost column.
Yeah, and then did you just feed the, well, I'm using the concept of time series here because, well, this is observation, looks like a time series. Did you just feed the input directly to MLP and trained it?
Well, so we trained the MLP just to do next step prediction, and then to validate the MLP, we used it autoregressively. So we used its current prediction, fed back to make the next prediction, and so there was it has the ability to drift like everything else.
So and then you used Koopman operator.
No, the MLP column doesn't use any Koopman.
No. I'm just talking about the first part. So for Koopman though, you're decomposing your input space, right? And then you use an autoencoder there.
Sorry, what do you mean by so an MLP you can consider it as decomposing the input space?
No.
Right?
I'm speaking of the feature extraction part. So for Koopman, you're doing feature extraction or feature engineering, right?
So we're not doing explicit, we're not like hand extracting features. Everything is learned end to end in all cases. It's just in the Koopman case, we have a regularizer that we introduced like an auxiliary loss, whereas in the MLP, we only have prediction as a loss.
My point is, well, if you put any model the way MLP is there, I highly doubt that direct forecasting or predicting even a step ahead, because I guess, correct me if I'm wrong, you are manipulating your input. And then you're forecasting with Koopman scenario.
So the input is quote unquote manipulated by a trainable feature extractor. And
yeah, but it's not the same for MLP, right?
Well, MLP has the chance to learn the exact same features. It has the capacity.
So my point is, do you have any comparisons other than MLP, let's say in terms of using an autoregressive model and Koopman operator, let's say? So not like MLP plain kind of thing.
So you mean like a transformer or something?
No, an autoregressive model is a statistical autoregression model.
Oh, like
Same.
ARIMA or something, ARMA.
No, just autoregress. Yeah, but just drop the moving average part. So AR, for example.
Well, so an MLP is just a generalization of this when you unroll it autoregressively, right? So you're training on a next step prediction, but in order to generate long sequences, you're just running it autoregressively. Does that make sense?
So it does and it doesn't, from what I'm looking at the problem. So if I think the comparison makes sense to me if the same concept has been applied initially for both scenarios. So I'm comparing apples to apples. So if there is feature engineering done for the first scenario, I want to see the exact same feature engineering performed for the second scenario.
So I disagree with that. There's feature engineering, there's loss engineering. They're trained on different losses, and one is using a regularizer, but it's not like we're literally designing features by hand.
So if they're trained on different losses, then how can we compare the errors?
So for example, if I say, in addition to doing next step prediction, I will also ask you to like introduce an alignment regularizer somewhere in your latent space. Like for example, sparse autoencoders, right? Sparse autoencoders could be trained on reconstruction plus sparsity, but they're evaluated on, for example, classification. And although that's not true, but they might work better than something directly trained on classification, right? So there are these comparisons in the literature.
Okay, so
Just,
I just want to understand.
Just like, let's skip the rest of the discussion.
I apologize. Thank you.
Just.
All right. Then we did some kind of like RL experiments. Well, Mahan did some RL experiments. So there's this benchmark, which is D4RL, which is behavior cloning. And so we kind of applied these things to much higher dynamical systems and sort of found similar results. So here we just do prediction in the state space, right? This is not pixels, but in state space of Majoko-like environments. Here we're just using like a L2 error to measure how well we predict far into the future in the state space. But then, you know, that still begs the question, like, okay, what does that mean? Like you're off by 0.08 or whatever in the state space. Is that useful? There's a cool evaluation that Mahan came up with that I really like, and that's basically introducing sparse feedback control. So here we have like a agent trained with behavior cloning. And here to evaluate how good our model is, so this is like sort of like model predictive control-ish, instead of getting feedback from the environment at every step as is typical in RL, right? So you do an action, you will take an observation. Here we're blinding the agent and we're only allowing the agent to use the model's predicted states. So basically a model of the environment rather than the true environment. And we're showing that, yes, of course, it's not going to be as good as observing the true environment at every step. But then we also beat like kind of other reasonable baselines for doing this. So basically, it's measuring state prediction in terms of reward as a metric rather than just L2. So like how good are your states being predicted? But don't tell me in terms of L2, tell me in terms of reward achieved based on an expert policy. Does that make sense? That's it. So now we can take questions.
So for Koopman, you need a complex K, right? In general, do you use complex?
No, just real.
Just wouldn't it make a difference?
The eigenvalues could be complex, but the matrix itself is real.
Jeffrey, you can ask a question.
Sure. So in general, so you have a deterministic, fully observable system, but in general, you might have a system that where your observation gives you new information. And these same problems that you're observing here, they're also present in systems that need observation. But you would have to somehow learn the filtering function. Do you have thoughts about how you would do that?
Yeah. So yes and no. So some of the points that I've tried to make only apply to fully observable deterministic systems. That's why I kept repeating fully observable deterministic.
Yes.
Like the whole thing
Like
about
no crossing.
Yeah, that's totally fair game if you have partial observability or non-determinism. So, for example, I always think back to like classical mechanics when I want to like come up with an example. So if you're assuming, deterministic classical mechanics in order to make your, you want to model the system, at some point if it's fully observable, it's also deterministic, and like you can roll forward the equations with no problem. So it's onto other algorithms or like, computer vision or something from video, you should be able to extract the full state, like everything you need, the position and velocities of all the particles that you care about. Like a good example is in the first slide, right? Like this is kind of facetious example to sort of like show the limitations of this kind of way of thinking of like, given the initial frame, predict the next or future frame. Like you had no idea this like 400-mile-an-hour billiard ball was being shot from the right-hand side of the screen of this thing, right? So this is not a fully observable system.
Right. But nonetheless, your observations here are potentially really useful for the okay, a lot of real physical systems become pretty darn close to fully observable if you give multiple frames, right? Atari is close to fully observable if you give multiple frames, but it's not actually completely fully observable. But yet your ideas really ought to help us learn a good encoder.
I think the ideas are mainly applied to like, once you're pretty sure this state captures everything you need to know and you just want to model the dynamics, that's where the ideas generally apply. But I agree, I need to spend some like more time thinking about like real world applications of like what's the like sort of killer app of this stuff.
Right. So in any case, this is really interesting. Thank you very much.
Thank you. Thank you.
Could you give some intuition about why it's not better to just like always re-encode like after every single step?
No, I have no idea. To be honest, like everything I'll say will be sort of hand wavy. I think we need to really do some follow-on work to investigate it. But one possibility that Clement Gehring like kind of raised is the encoder and decoder are not perfect inverses of each other. So maybe it's better to like use it sparingly to rely on that inverse. So that introduces its own noise. So you can think of it as like a reprojection error. And then you accumulate not only like the wrong dynamics error, but also like reprojection error. So maybe the periodic re-encoding, also the fact that it's periodic and not at every step, has to do with the encoder and decoder not being perfect inverses of each other.
Okay, so I guess the intuition is that sort of mixing different sources of error maybe makes it not accumulate as badly, kind of.
Yeah, maybe.
Something like that. Thank you.
Yeah.
Hi, I was wondering, so you mentioned that the Koopman operator assumes that you have some, or like you're modeling some like infinite dimensional latent space. But here, obviously, we have to use something of finite dimension. Have you looked at how like performance scales as you change the size of the dimensionality?
That's a very good question. I don't think we did like a super duper thorough investigation of this. We fixed our like latent dimension, but some of these conclusions, one thing I forgot to say, you reminded me, like the whole thing about lines crossing, that will stay. That is mathematical truth, fact. Even if you raise the dimension or give the model more capacity, I hope I've convinced you that like some of these problems will persist. But yeah, no, we haven't really thoroughly investigated like the effective dimension, latent dimension.
All right, I might transgress Rim's rules here, but I was wondering if you've thought about evaluating the error between the encoder and decoder as an average over the space, and how this might inform you as the period as when you need to re-encode, right? So can you get a signal from that mismatch in the autoencoder part to actually inform you to the optimal period?
Yeah, that's a very good idea. Of course, it's a training time idea. You can't do this as test time.
Yeah, it says, yeah, chicken
not
or an
an
egg, right?
online-
Like
it's
it's
not
you're
an
training
online.
both at the same
Yeah,
time.
yeah. I also think that maybe in addition to that phenomenon, what we have found, because we tune the re-encoding period for each system, different, so it's different. And I believe what we found, like maybe Mahan can correct me if I'm wrong, but the ones with higher curvature, like higher Lipschitz constant, will need more frequent re-encoding.
That's exactly, yeah, that's the intuition. If you have a high Lipschitz constant in your autoencoder scheme, then you'll need to up your
Yeah, but
periodicity.
also that's reflected in the original equations.
That's right, exactly.
Yeah.
But you can actually, then the follow-up question is, you could have an adaptive periodic re-encoding, right? Like depending on where you are in state space, you might, afford to stay in Koopman space for a while.
Yes,
and then,
yes. We have a little thing in the paper saying this is like someone could do this maybe.
Okay, future work. Okay.
Yeah,
Cool.
exactly.
Thanks.
Any other questions?
Just a question about the decoder. Could you just please explain what were the conclusions about the shape you should have, please?
Yeah, so empirically, so there are two things that I can say about the decoder. One is sort of in the toy example. The toy example involves a linear decoder. And also empirically, we found that the best performance is to use a linear decoder. Now, whether that implies that the toy example is really what's going on in reality, I don't know. I don't think it's safe to jump to those conclusions. But just to give you an intuition, a nonlinear decoder has the capacity to kind of cut the space up, the latent space, and sort of do the kind of like sort of sparse coding trick of cutting up the space and applying different mappings to different parts of the space. So it can, in theory, learn to synthesize very complex dynamics if you give it that capacity. What's interesting is in our experiments, even though we've given it that capacity, we failed to see that it uses it effectively.
Okay, but in the RL experiments, the decoder was nonlinear. If I understood well.
In the
It's the best performing
RL,
one.
in the
because of inside.
RL, so
Yes.
DFRL, nonlinear. Oh yeah, for the RL experiments, yeah, the best thing was nonlinear, but for the low dimensional ones, the best thing happened to be linear.
Okay.
No idea.
Thank you very much. Thank you for the presentation.
Thank you.
All right, let's thank Russ again.